My name is Nicolai. I am a PhD student at Higher School of Economics, and I'm also working at Space Research Institute in Russia. So in this talk, I will discuss the application that is a leading developer of this project called Aware for some reason, and it's designed to process alert messages from GCN on astrophysical transients and planning their observations with optical telescopes. So the outline of my talk is given here. For this project, we set some requirements. First of all, we want to process the alert messages from the GCN Kafka cluster, which is new type of connection to the GCN now, and we want to extract the necessary information on these transients. We also want to share this information in human-readable format with the Telegram subscribers. We also want to perform the planning of the observations with optical telescopes and share these observation plans with subscribers too. And we also want to be able to operate in real time, at least for messaging functionality. The objects of our interest are fast variable rate cosmological transients. One of the previous speaker has covered this topic, so I want to skip this. For optical follow-up of transients, there are two tactics involved. The first one is the tile observations. It's showed on the left-hand side. In this case, the wide field telescopes scan the localization sky map of the transient, and the performance of this scanning depends on field of view of the telescope, the exposure time, and the slew rate. The other method is which is completely different from the tile observations, is target observations. Here we want to observe candidate host galaxies on transients with narrow field telescopes. And of course, one can combine these tactics together for some heterogeneous network of telescopes. When speaking about target observations, I could not avoid the case of GW-170817. It's a great example of carrying out the target observations, since it was the first time when the astronomers have ever detected the optical counterpart to LIGO Virgo event. The localization sky map was about 26 degrees squared, in shown in the left-hand side. The observation was carried out using a slope 1 meter survey, and the transient was detected about 11 hours since the gravitational wave trigger. The transient was located in the wing of the host galaxy in GC 4993, and it's located at a distance about 4 megaparsec from the Earth. For the needs of target observations, astronomers have compiled a special catalog. It's called GLADE Plus, which stands for Gravitational Galaxies List for Advanced Detectors. This catalog has a lot of fields. The density over the whole sky is about 500 degrees squared. However, if we take into account the LVK estimates to the gravitational wave source, we can have a number, the density number, about a few degrees squared. We put constraints on the distance as shown in the low left corner. The right border is larger than the left one because the completeness of GLADE Plus decreases with distance, as shown on the right-hand side. When speaking about observation tactics, of course, we mentioned distributed network of telescopes. In our particular case, GRB-IKI follow-up network. Our facilities and collaboration are shown on the map on the right hand side, and the complete list of the facilities listed in the on the left hand side. In order to plan for such heterogeneous network, we're developing the software they call AWARE, and its flowchart is shown on the slide. The application is actually a Python executable module with 2 threads of execution. The first thread is a planner. It processes alerts, plan observations, and create messages. Then it puts to a synchronous query to the Telegram bot, which actually sends messages to subscribers and react to subscriber commands. The software has a YAML configuration. It has a simple database for storing the alerts and also storing the subscription settings. Plans and plots generated by the planner stored on the disk. The main stack is shown in the lower left corner. Let me review these projects, and I want to start from messaging capabilities. Everything starts from receiving the raw VO event from GCN cluster. Actually, VO event is a simple XML file, but with different header. And then, according to the message topic is assigned actually to different instruments. For example, on board the spacecraft or LIGO, Virgo, KAGRA instruments. We're parsing these events. We're extracting the necessary information from these events. Then we perform cross-matching coordinate space and time space with already stored events in the database. The reason is because different instruments label their label events according to their own schemas, and we want to actually send updated localization sky maps for these events. So we decide to after cross-matching, we decide to run the planner if the localization sky map is greater than already stored in the database. So we do not run the runner, run the planner. Otherwise, we run the planner, make plans, and send them to the subscribers in the Telegram. Okay, so now I'm going to talk about the Telegram bot. Its flow chart is shown here. Telegram bot is completely asynchronous. It has several commands. User can subscribe or unsubscribe from the bot. It can actually have can view its subscription plans. Also, one can retrieve a finding chart using SkyView and DSS2 surveying the filter R. Currently, this bot running in a long poly mode. Here, you can see the results of the planning for a test alert from LIGO Virgo KAGRA. On the left, you can see the message generated in a human readable form, and in the middle, you can see the coverage map by certain telescopes for the first epoch of observations. And on the right, you can see the generated plan for this epoch. Actually, we have 2 formats. Here, the plan is stored as a simple ASCII table, but also we support .list format, which is available for telescope operated under Foreign House or KDS proprietary controlling software. So how we decide to make plans? First of all, if this LIGO Virgo event, it should has a false alarm rate less than 10 events per year. It should has 1 neutron star in the binary system and has a area under 300 degrees. or it can be a binary black hole merger with a 30 degrees squared or less area. Then we automatically generate plans for the first night of for the first epoch of observation, and send these plans to board.
2 minutes.
Okay, great. So now here we see the so I want to review algorithms of planning. So here we have the tile version planning. We just regrid the sky map in the tiles. We find first significant tiles and go to the least significant tiles. Here we have some sort of spiral trajectory without sharp transitions. A bit the same algorithm we implemented for the target observations is shown here. So here we have the result of our planning for real events in current LIGO Virgo KAGRA run. And on the left is a neutron star black hole merger. On the right is a binary black hole merger with a 30 degrees area. So to sum up, we are developing the open source solution that allows one to retrieve alerts from the GCN, process them, and send to users in a human form, perform planning of these events. We implemented both observational tactics. We're planning for LVK events and for regular GRBs or other transient from GCN. And DAWARE is on duty at Space Research Institute. We also want to implement further features for this project. For example, custom threshold, per alert type, moon separation, etc. You also can suggest your own feature. Thank you. You know, these projects is open source. The link is shown here. Everyone welcome to suggest your own feature, something like that. Thank you.
Thanks.